before we get started, I'd like to do a review of how we calculate gradients. So analytically from calculus, we know how to calculate gradients using calculating derivatives. In that case, you say del f by del x, and for polynomial functions, it's an easy formula where we take the power. So it becomes 2 times 5, and then x is 5 minus 1, and then similarly, you do it here, and you get 8 times x plus 9. This looks like 10x times x to the power 4, 8x plus 9. But if you were to solve gradients numerically, because a lot of the times you're using functions where the gradient is not easy to calculate, it wouldn't be a polynomial function like this. In those cases, it's often much more easier to calculate your gradient numerically. When we mean calculating a gradient numerically, we mean at about a point. So let's say this is our function and we're trying to calculate the gradient. So it will be about this point. And we'll calculate it according to the rise over run formula. And there's 3 ways of doing it. One is forward difference, where we look at a point in front of the point, so this and this point, and we calculate the slope. The backward difference, where we would look at our point and a point behind that point in the x direction, that becomes the backward difference. And then the symmetric difference is what you'd guess, looking at a little bit in front of your point and a little in back of your point and getting the slope of that. In most cases, that would be your best estimate, but that's not always true. So that's an easy way to do it. And like numerically, if you were to see something like that in code, we would go about doing it. So for analytically calculating stuff in the code, we're going to need to use the symbolic package in Julia. So we're going to using SymPy. Then before we do that, actually here is where I'm doing it analytically. So first step to do it is you call a function vars, which declares a symbolic variable called z. Then you create a symbolic function of the variable z. It's the same as this one. And then to make that symbolic function, to differentiate that symbolic function, we use this diff operator. And then to get the value at a particular point, so let's say we want to find out the value of our differential at the point 1, we're going to use the substitute function. We can also see our function, that is the differential. It looks like, oh, my bad. So it looks like 10z to the power 4, 8z plus 9, which is what we calculated here. It's pretty easy to see. And we use the substitute function to substitute values into symbolic functions, which gives us the value 27 at some point 1. So let's see what that means when we try to do it numerically. So we define a function in x. This is not a symbolic function. It's a normal function. And then let's get the code for calculating the differential. So if your difference type is symmetric, then you want to give out the value f of x naught plus h minus f of x naught minus h divided by 2h. And brackets. Otherwise, if your difference type is forward, then you want to return f of x naught plus h minus f of x naught by h, and let's assume the default is backward difference. So you want to give f of x naught minus f of x minus x naught minus h by h. So that gives us a function that will calculate the differential. Incomplete function. Oh, I forgot an end. What if we tried to plot that function? Take time. So the function kind of looks like that, and we're trying to calculate the gradient at this point at x equals 1. Analytically, we saw the value to be 27. Let's look at, so essentially the function gives you a slope, right? So used in, what? So what this will do, so this is our symmetric difference. We got the slope of the function to be 49. And that depends a lot on our step size. If I changed my step size even by a factor of 10, my slope is 0.27, that tiny thing on there, which is a lot closer to the value 27 if you scale it properly. But for visual representations, let's take this one. Similarly, if you plot the forward difference, it looks like this. It's not really very correct with that step size. And then with the backward one, it looks like it's probably the most promising one. So there's no way of knowing which one will be the best for your problem. It depends a lot on your step size and your function. It's always a good practice to plot things and see what your gradients look like. And that's all about gradients that I want to go over. Do you have any questions for me, or should I move on? I will move on then. So now that we know how to calculate gradients analytically, numerically, using the symbolic math toolbox, next thing is we want to use these gradients into finding minima of functions. So like we learned in class, there's two problems that come under this umbrella. One is when your minimizing variable is a scalar quantity. So that would look like when f of x is just a function of x and x belongs to the real numbers. It is not a column vector. In that case, we can just take a step. Gradient descent will basically just take a step in the direction of the decreasing gradient of that function. And theoretically, it's easy to see that you'll eventually converge to a point that is of minimum value. This becomes more interesting, though, when we're looking at problems in dimensions more than one. So then, in this case, your x variable will belong to a column. And we define our gradients by this triangle value, and this is pronounced as grad of f, which is basically grad of f is the partial derivative with respect to all dimensions of x. So let's say x belongs in n dimensions, is an n-dimensional column vector. Then grad of f of x will look like del f by del x1, del f by del x2, to del f by del xn. And it's a column vector, actually. So I'll put a transpose here. And from there, we get our update in x to be a step size of the decreasing gradient. So because this is a row and then we make it a column, so then it becomes S transpose grad of f of x. If that formulation is clear, we can look at an example. So let's say you were trying to minimize this function in R2. So in this case, x is in R2. And we know the update rule is this. So the first thing we'd want to do is calculate the gradient. Let's see how you would do that in Julia. So I was going to use this question as it is, but we can go over the code if we like. So calculating gradients.
I have a question. So, I think you said just a little bit ago that so is the gradient a column or a row vector?
So the gradient is a row vector, but then when we're multiplying it, it becomes a column. So x is a column, so x is say two-dimensional. This will be two-dimensional. S is just a step size. So we want something that is a column, but when we calculate it, it becomes a row. So yeah, let's.
Awesome, cool, thank you.
Yeah, and then that would become column. And then for each of these values, you'd want to have gradient with respect to x1. So that's basically your function, your value of x minus h times 1, 0, 0, however many zeros, minus, this will be x plus, and then x minus h of the identity by 2h. That becomes the first element of your gradient. It'll be easier to probably see in code. So let's say you want to calculate a function, and let's call it calculate gradient of any function f at a point x0. So first of all, we know what the size of our x should be. So let's get whatever is the length of x0. And then you want your gradient will be of the size, you want it to be a row vector, so it'll be of the size zeros, 1, n. We initialize it with the value 0. And let's say your h is some 0.01. So then we want, this is for R2, let's say, or let's keep it general. So for I equals 1 to n, you would fill out the first column of your, the first column of your gradient will be 1 comma I equals f of x naught plus h times the identity. You want the identity of the size. So let's call it my identity is I plus zeros of n comma n. And then you want to get the ith column of your identity. That becomes the E1, E2, E3. So you get the ith column of your identity. You add that to x1, then minus f of x naught minus h times my ID by 2 times h. So let's run. This is our function, and we want to see the gradient, let's say at x naught. That x naught is good enough. So calc grad of the function and x naught. Oh, I forgot to return. The gradient at x naught looks like this. What does that mean? So let's look at the contour plot for this thing. So basically at x naught, that is this point right here, which is 10 comma 10. So the point, this point here, the value of the function is around, I think that's 650. And the gradient should be in this direction. So right now, well, it'll be more of an abstract concept. Let's say you have that gradient. You're going to want to unexpected end. That makes more sense. Okay. That is basically what this function is doing as well. Then you want to do gradient descent on this. So you want to use that gradient and increment your x values using this update rule. So let's see, we'll define the damping ratio around 0.1. What else do we need? We need h. We need our gradient to be calc. And we'll give it our function and the point x naught to begin with. And I'll initialize a variable xk with x naught. Then you go into the while loop, and we're going to be inside the loop until the norm of our gradient is greater than, say, e to the power minus 5. Let's also keep track of our iterations. So start with 1, and let's say we want to stay within 10,000 iterations. So we started with the first estimate. Let us let's update. So then xk equals xk minus the s times the gradient transpose. Then you want to recalculate the gradient at the new xk. So then your gradient equals grad at the xk point. Update your iterations. And for plotting purposes, I'm using this code to keep track of my x. So let's see if this converges. It did not converge. Okay. So let's try with a no. There's probably something wrong with the gradient function. If I use the one from class, something's up with the gradient function we just wrote. Let me check. This thing. That looks right. X naught. So it should be minus that. Oh, I missed a bracket there. Okay. So we can use that function that we had. Cal grad. So to see how we're descending down the gradient, let's try and plot these values. I'm going to copy my code so that I don't make a problem. So you want to scatter, plot x. The x value is the first one, and then the y values are in the second row. We'll get the color is black. And also want to see the line. We started from there, and we wanted to get xk in here. And it looks like that. So we started from here, and these were the different points that we changed at, and we finally converged at this value in the center, which probably has the least f, the f of x is the minimum. So it's somewhere around 0.1 on the x and 1.12 on the y. Did that plot confuse you, or was it clear how we're going down the gradient? Can I assume it was good? Okay. And we can see how it changes with our step size. So let's say we wanted a smaller step size. It's a much smoother fall down the gradient around at each point. So that's basically how you would end up doing gradient when you're given when you're optimizing over a vector. If that is clear, we'll move on to Newton's method. So in Newton's method, we look at the Hessian, which is basically a second order derivative of our function. That's easier to see when the function is a scalar, where we end up doing just the inverse of the second order derivative and update it as so instead of putting the dam value, we get the second order derivative, inverse it, and you multiply it with the gradient. And then you do the same for the vector optimization. So this will essentially become, if we weren't using LU factorization, you'll have delta xk equals the negative of the inverse of your gradient. So f of xk. This is matrix inverse times transpose of our matrix, of our gradient. The dimensions of this, so if x is in Rn, the gradient of f of x will be also in Rn, but it will be, let's say, Rn. It will be a row vector. And then the Hessian would be in Rn cross n. It will be a square matrix. How does it become a square matrix? Well, when we're calculating the Hessian numerically, what we end up doing, so let's say x is some x1, x2 to xn. Gradient of f of x is defined as del f1 by del x1, del f, that's a single function, del f by del x2 to del f by del xn. We take the transpose of this and we get a column vector of our gradients. And then we further apply a gradient to this process. So applying gradient again just basically means that we're going to do a partial differentiation with respect to all, with respect to each dimension of x. So that becomes del f by del x1, del 2f by del f1. And then this one will become del 2f by del x1, del x2, and so on. This becomes del 2f by del x1, xn. And similarly, this becomes del 2f by del xn and del xn. And we're doing it numerically. We want to get, let me put it, numerically, we will approximate this. We will approximate del f by del x1 how we normally do. We'll have f of x plus h of e1 minus f of x minus h of e1 by 2 times h. And then for the Hessian, we get each term del x1, del x, let's say 2. We'll have f of, so we're taking this term and then differentiating it with respect to 2. So then with each of these, you'll have f of x, h e1 plus delta e2. This is just looking at this part right here and differentiating it with respect to the second variable, minus f of x plus h e1 minus del e2, this whole thing. And then you do the same here, get minus f of x minus h e1 plus delta e2, and then minus of minus is plus, so this becomes f of x minus h e1 minus delta e2 by 4h delta. And then we build all of these terms together, and that becomes our Hessian. This is a lot harder to do as a drill problem, so we're going to look at it in code. So we were given this function grad Hess. Let's say it's basically written down for us, but let's say, should we write it down? I think it's pretty obvious. So we got the grad part down in our calc grad. It's the exact same thing. With the Hessian, we initialize our Hessian with a zero matrix of the size n cross n, because we noted that the size of the Hessian is going to be n cross n. And then for each term of the Hessian, you calculate the differential using the formula HE1 plus delta E2, which is 1 and 2 in this case being the first index and the second index. You use the formula that's directly written down in the book, and you finally have the Hessian. It's just an application of the same. And then you return it, and that's what this function is going to do for us. Where we use it in this calculation. So because it's a smaller problem, we can just use the inverse of the Hessian, multiply it with the gradient, and use that as an update of our variable x. So let's try to solve this problem using Newton's method. So I have my x naught at 10, 10. We saw what the gradient descent did. Let's see what the Newton's method will do. So I'm going to initialize my gradient and the Hessian using the function grad S of f comma x naught. Reinitialize your xk. Reinitialize the number of iterations and the values of x. And then you want to continue till the norm of your gradient is greater than 1e minus 5, and the number of iterations are less than 10,000. Same thing. Then we update our xk using xk minus the inverse of our h times the gradient transpose. Update your gradient and the Hessian at the new x. Update the iterations and save the values. So let's see how much time Newton's method takes. And it converged a lot faster. It took 5 iterations, and this one took 840. Let's see why it looks the way that it does. So I'm going to copy this plotting code from here. And this is going to be Newton's method. And the color can be blue. Let's see. So the Newton's method took the shorter way instead of going down the gradient like that, because we multiplied with the second order differential. It went down directly towards, it converged faster towards our minimum. But if you look at that, it's not very smooth. A lot of the iterations are at this point. So in practice, we end up using a damped version. So looking at this, you would say this was with a step size of 1. We did okay, but we might want a smoother curve. So let's say you'll go for something like 0.7. Update it here, and it looks like this. So it's a little better. I think we might want to go for like 0.5 maybe. And that looks a lot smoother. So let's see what our final plots look like for that function. So we used a step size of 0.01 for a smoother curve and gradient descent. The number of iterations was 840. This was our solution. And then for Newton's method, we converged in 25 iterations. And this is the path we took to converge to our solution. But the solutions are going to be comparable. I think the values are pretty much comparable. And that's the gist of it, I think. The next example is how you solve regression problems that I was going to take. But if you have questions for this toy problem, you can ask me now, or we can go over the next problem. Is that okay? Is that clear? Okay. So another problem that we looked at, right back in. So how we related it to regression was in regression we were given a set of points and measurements. And so it looked something like this, and we were trying to fit a line through these points. And the way we posed our problem was that we would get a matrix phi that would be our support vector. And for a line, it would look like all the values of x, so x1, so it would look like everything in the variable x and all ones here for the phi matrix. And then our alpha star was the slope and the intercept, and then the y was just our measurements y. And we were trying to solve for the minimum norm solution of phi times alpha star minus y. This can be written down, this norm can be written down as phi times alpha star and square root of the norm minus y transpose times phi times alpha star minus y. So again, this is a minimization problem. And the way that we solved it was getting the minimum norm solution to be phi transpose phi inverse phi transpose y, and that would give us our alpha values. And that we somehow convinced ourselves was the minimum norm solution. We can pose the same problem. Just because it's a minimization problem, we can try and solve it using both gradient descent and Newton's method, and we'll see that the answer pretty much looks the same. So this is the example problem from chapter 8. We had, let me split the cells. We had x and y, and it looked like this set of points, and we were trying to fit a line through it. The way that we solved it, we said alpha star equals inverse of phi transpose times phi transpose times y, and then our y hat was equal to phi times alpha star, and we would plot our x with y hat on the same plot, and it looked like this. And somehow we convinced ourselves that the alpha star was giving us the minimum norm solution. Let's see if we can get the same value of alpha star using gradient descent. So first of all, let's see what the contour plot looks like. So I'm going to choose the slope values between 0 and 4, and then b between minus 10 and 10. And we're trying to find the minimum norm. So we're trying to minimize the function. I had to write it two ways because of the difference in plotting, but it's the same comparable function. And that is given by the norm of phi times alpha star minus y squared, which is basically this norm right here. And we're trying to minimize it. So let's see what the contour plot looks like. So we see that it is kind of a convex function. Everything on the edges has a value of around, I think, 2,000 here. And then as you move closer, all these circles get like smaller and smaller and smaller. So then somewhere around here in the middle, there's probably a minima. And that's what we're going to try to find. So we have our initial guess to be m is between 0 and 4, and b is between minus 10 and 10. We saw from here that m is actually 2.12 and b is 2.33. And we should be able to converge to that. So I'm going to start at a point 3, 10, so right about here. And that's actually, we can just copy the code for both of those things. So copy this. And this will be gradient descent. Let's see. It took 817 iterations, and it went kind of like in a zigzag manner. So when you see something like that happening, that basically means your step size is too big. So when you're trying to converge, you're taking too big of a step. It'll still converge like it did, but you're taking too big a step in your gradient. So I want a much smaller step size. So let's say 0.001. And that looks a lot better. Let me recreate the contour plot so it's easier to see. And it converges smoothly along the gradient towards this value in the center, which is probably the minimum value. And we could converge from gradient descent. And the values, if we compare it with alpha star that we had, so is approx xk comma alpha star, and the tolerance is, let's say, 0.001, and that's true. So we got the same solution from the minimum norm solution and also with our gradient descent, and that makes sense. Now, if you want to see it go faster, we will use the Newton's method. Just copy the code, paste it here. We might have to adjust our step size, but Newton's method, because it follows a pretty good direction, you usually don't have to worry about it. And most probably the solution is going to be the same. So I can copy this, and it should return the true value. And the number of iterations was a lot smaller, so 27. And that's pretty much, I think, all we need to know about these two methods, gradient descent and Newton's method. If you have questions, you can ask me now. I'm going to post these notebooks on Canvas right after we're done. So you can make these plots for yourself. Questions? I'm going to end this early because there's not much to do after this. Is that clear how to set up the drill problem, or should we go over that? Okay.
Do you think we could go over number 5 in the drill problems?
Mm-hmm. So, number 5. So you want to calculate the gradient numerical approximation of the Hessian for the function at a given point.
Mm-hmm.
And you're given the formula. So let's see.
Does this like have to be on paper, or are we allowed to do it in Julia?
It'll be exactly how we do it in Julia, and it might be easier if you do it in Julia actually. So let's see. You're given the function f x1 comma x2, and your function is x2 times sine of x1 plus x1 x2, and then you give the point x0 equals pi by 2, and you have to equals -1. And then you want to go over, so your your x is 2 variables, right? So your Hessian should be a 2 cross 2 matrix. So the first loop will go from 1 to 2, and the second loop will also go from 1 to 2. And then initialize your Hessian to be zeros of 2, 2. And then each term in here will be equal to that formula right here. So let's define E1 first. So E1 is this vector, and E2 is this vector, which is basically different columns of the identity matrix. And then you define H to be 0.1 and delta to be 0.1. And then we're just going to use this formula. So our formula is f of, actually we'll have to keep it x. Then this becomes x of 2, because it's in vector form. It'll be easier to keep it like this. x1, x2, and then your x0 can be 5.2 and -1. So then each term in here is given as f of x plus h times e so it'll have to be I. And then from here you can get E1, E2 using the identity matrix. So you get the ID, and you'll get the ith column plus delta times the jth column minus x plus ek, and there's a minus here. It's basically just substituting that formula and just knowing that your EI and EJ are basically the ith columns of the identity matrix.
Mhm.
And you can do that as, and then minus of, just going to copy it. It's probably x minus h plus delta, and then plus of this thing, and minus delta. And put this whole thing in a bracket and divide it by 4 times delta times h, and that's it. dimension mismatch. In line 8, that makes sense. So I might have missed bracket or something here and there. This is x naught, x actually. Yeah, and that's your answer basically. Is that clear? Are you asking me how that formula came about, or?
Well, I saw the formula and like I don't know, like I was just kind of confused as to like how to like plug into it really. Like I
So
don't know.
the formula
Like
basically is like gradient of a gradient. So for all gradients, you add a small number h and you subtract the same, and it's doing that twice. It's basically like a function of the same function. And that's how you get that formula.
okay. What's that one like kind of like squiggle like circle thing that kind of looks like a D? Is it like an epsilon? Like what like Greek letter is that?
Oh, that's called a delta.
Oh, is that like
Yeah.
lowercase delta? Okay.
So
Oh, okay.
that's the small delta, and the grad function, when you invert it, then becomes like, that's the big delta.
Right. Okay.
Yep.
Sweet. So yeah. Awesome. Thank you. I also have a question like uh so for the Julia homework, the last part we need to solve for delta x and we don't really have access to like the previous Julias where we can like do like QR factorization to solve for x. Is there any way that you guys can make it so we could fetch the feedback from those and then like copy and paste our code from that? Or
So you're missing the feedback on homework 8?
I don't know which homework it was exactly, but whichever homework we did where we solved like for x star using like QR factorization or whatever.
Yeah. Why don't you send us an email about this and we can fetch feedback for you? That's easy to do. We can release feedback again.
Okay, cool. Sweet.
Yeah.
Is there what's like the easiest way to solve for like x, I guess? Is QR factorization the easiest, you think? Or
For what problem? For
so
the.
the very last part
Well, I
of the
mean,
Julia
the
homework.
way that we did right now, we just used the inverse. Because it's a small problem, you'll be okay if you're just using inverse. I don't think they're gonna be deducting points for that.
Okay. Wait, so when you're using the inverse, like could you like go like so like when you're using the inverse, do you just multiply it like it by the inverse? Or because like I tried to use the inverse and I got dimension mismatch.
So you
So
tried using the inverse, and what was the issue you had?
like dimension mismatch or something like that.
It was a dimension mismatch. That shouldn't be. So check if your Hessian is actually a square matrix, and also check the determinant of your Hessian. I'm pretty
Okay.
sure it should be differentiable. It should be invertible.
Okay, cool. So yeah, so does it matter the order uh what multiplies by what first?
Yes.
I think
So
it's like would it be like the I think it's like grad like the like grad squared or no transpose a grad times the inverse of Hessian. Is that right?
your grad transpose will be of the dimension n cross 1, and your Hessian will be n cross n, which will eventually give you n cross 1, which is the dimension of delta x, right? But if you did minus delta of the grad function first times the inverse of the Hessian. Then this would be n cross 1 times n cross n that you're trying to multiply, which is not, doesn't make sense.
Okay, that must have been my problem then. Okay,
Yeah.
cool.
Yeah. So whenever you have an equation like this and you're inverting it, the way to go about it is pre-multiply with the inverse on both sides. So if you have this equation and you're trying to invert it, what you'll do is you'll multiply with the inverse of the Hessian on both sides, and then one side will become the identity, and then the other one will have it on the right side. Data. And this one is also the inverse times f of xk, and then the gradient. This becomes identity, and then you have the equation delta xk equals inverse of the Hessian times the transpose of the gradient.
So do we have to get rid of the identity matrix, or are we allowed to just, like, I guess, pretend it doesn't exist?
We don't, so identity matrix multiplied with xk will just be xk, right?
Oh, yeah, so then it's fine.
Yeah.
We don't have to, like, solve.
That's why
cool.
Yeah, to get the identity there, we multiply with the inverse on that side.
Okay, sweet.
Yeah.
Awesome.